let's say I have a little ball. Okay, a little ball here on Earth, somewhere above the ground. Let's say that's my ground level. Now there would be a force pulling this ball down. That's the weight. I'll call this mg, mass times acceleration due to gravity. Mass, the m is the mass of the ball, g is usually taken as 9.81 meters per second squared. And m is the mass. Let's say the m is the mass here is 0.5 kilogram, for example. Then that's the mass. So this is something we are familiar with. If you have an object with this mass, there's a weight pulling it down. Now let's move this ball around. Suppose that I move this ball from here to here, right? To a higher place. Now I would expect that the weight is the same. Okay, so if a ball weighs a certain amount here, if I stand on a chair, it still weighs the same. If I go up to a higher floor in the building, it still weighs the same. But what if I do something quite extreme? I put this ball on an aeroplane. So I have an aeroplane flying in the air, maybe hundreds or 1,000 meters above the ground. Okay. If I have a ball in the plane, and this ball has the same mass, we would still expect it to have the same weight. Now let's do something really extreme. I'm going to take this ball and put it in a spaceship, and I'm going to take it all the way to outer space. Now let's look at this situation. When the ball is really far out and I look back on Earth, Earth would look like a ball itself. If that's my Earth, that's Earth. And the ball is a long way away, maybe that far away, as far as the moon, or even further. So I have a ball here, really far away from the Earth. How far? Well, okay. Let me say a distance. I'll use the symbol r to represent this distance. Say from the center of the Earth. The center of the Earth to the center of the ball. Let's say this distance is 100,000. Let's say it's 100,000 of a kilometer. That's a huge distance. Okay, I still have the ball still has the same mass, 0.5 kilogram. Now, what is the weight of the ball? Does it even have a meaning? Can we even still talk about the mass, the weight of the ball? Well, we all have an idea that if you are that far out in space, things are weightless. They don't have any weights. If you are away from Earth in outer space, things have no weights and things float around. Okay, so we would expect the weight to be zero, or maybe extremely small. So we have an idea that the further an object is from Earth, it should get lighter as an object gets further from Earth. Now, what I like to do now is I like to find out how to calculate, if I can still call it a weight, maybe a force. Right? I'll call it a force. I won't write mg for now. Just call it a force. We would expect that as you get further and further away from the Earth, the force from the Earth, or what is at first the weight, will get smaller and smaller. And if you're really far out, then maybe there's no more weight. Maybe the weight goes to 0. But if I'm at a certain distance from the Earth, is there a way to calculate the force from the Earth? There is, and this is called Newton's law of gravitation. Let me write this down. The way to calculate it is this formula. F is equal to G m over r squared. Now, the big M here is the mass of the Earth in kilogram. Little m is the mass, still the mass of the ball. Now, r is the distance. R is the distance from the center of the Earth to the center of the ball. And of course G, yes. G, the big G there has this value. It has a very small value actually. It's 6.67 times 10 to the power of minus 11. And the units for G is a little complicated. It's meter cubed, kilogram minus 1, and second minus 2. Now usually we don't need to remember these units. We just need to know that if we are using SI units for mass and distance, that would be kilogram and meter. As long as we are using SI units, we would use this number, which we can look up in some tables. Okay, right, so we usually don't have to actually remember this, but if we need to remember, if we need to know what the units are, we can work it out from the formula, and I'll talk about that afterwards. And for now, let me see how I can use this equation to actually find the force. Now, but before that, let's write down the names of these things. Now, this equation has a name. It is called Newton's law of gravitation. Newton's law, as in Newton's 3 law. Newton's law of gravitation. There. Okay, and this big G here, you have to be careful. That is not the same as the small g, whereas the small g is called the acceleration due to gravity, or acceleration of free fall. The big G here is called the gravitational constant. The gravitational constant. Okay, and it's a really small number, as you can see, 10 to the minus 11 in SI units. Now, if I want to use this formula to calculate, in this case, the force on this object, or you can still call it weight if you like, the gravitational force on this little ball at this big distance from the Earth, how would I do that? Well, I would put in all the numbers I know. Now, but if you look at the numbers that I need, so far we have big G, we have small m for the ball, we have the radius, but we don't have big M yet. We don't know the mass of the Earth yet. Now, I just went to Google and looked up Wikipedia just now, and I found this value for the mass of the Earth. It's 5.97 times 10 to the power of 24 kilogram. So that's a huge number, and that's the mass of the Earth. So no wonder we feel all this gravitational force, and the Earth is so massive. Then now that we have all the numbers, let me just write out what we need in order to calculate the value for this force on the ball. Starting from the G, we need to substitute in this number 6.67 10 to the minus 11. So 6.67 times 10 to the minus 11. That's G. And mass of the ball, of the Earth, for the big M. So 5.97 times 10 to the 24th, and mass of the ball, that would be times 0.5 over radius, distance squared. Distance is 100,000 kilometers. Okay, so we have 100,000. Now, remember that for this formula, as it's often the case in physics formula, though not always the case, but for this formula, we need everything in SI units. So SI units means that the kilogram, 100,000 kilogram, I have to multiply it by 1,000 to convert it to meters. And we mustn't forget the square. We have to square this number. So once we have it all written down in this way, we can use our calculator to find an answer. Alright. Now what you can see here is that you can try this out for yourself. You will expect that the answer to be very small just by looking at the powers here. See, you have a minus 11 there. Okay, you have a power of 24. Okay, that's a big number, but we also have a big distance. If you look at this, you see 1, 2, 3, 4, 5, 6, 7, 8. The 8 zeros, you square that becomes 16 zeros. Right? So you have 16 zeros at the bottom, and your power of 24 on top. So if you subtract the powers, you get 24 minus 16. That's 8 zeros on top. But then you have the minus 11 there. Right? So you would minus that 8 zeros. From the 8 zeros, you take away 11 zeros. That gives you minus a power of minus 3. Power minus 3, and you have these two numbers multiplied together. So just by looking at this number, a quick estimate would give an approximate value, right, without actually doing using the calculator, which you could do. Of course, I'll probably get a weight of around 10 to the minus 2, which is maybe about 0.01 of a Newton. So that's a small, very small force. Now, compared with what I expect here, if I just do a rough calculation, that's the mass is 0.5 kilogram. When I'm on the surface of the Earth, the G here, 9.81. So if I take it to be roughly 10, so 10 times 5 is 5 Newton. So from the 5 Newton weights that I have when I'm standing on the ground, on Earth. If I take it away as far as 100,000 kilometers away from Earth, then the weight becomes just a tiny 0.01 Newton.